Welcome back, it's Mrs. Hofferberth. Let's talk about calorimetry. Calorimetry is an indirect method for measuring the amount of heat transfer. Often we're interested in how much heat is given off by either a chemical or a physical process, but we can't easily measure that heat directly. We can't actually measure exactly how much heat that's releasing for a variety of reasons. And so what calorimetry is going to do is it's going to allow us to easily measure the heat that's gained or lost by one material, usually a cup full of water. And if we know how much heat was gained or lost by the water, we can use that to figure out how much heat was gained or lost by the material. This is simply a statement of the law of conservation of energy. This idea that energy is neither created nor destroyed, so if something loses energy, something else has to gain it. So, for example, if we have, say, a hot cup of tea, if that hot cup of tea loses 500 joules of heat, then the surroundings must have gained that much heat. And so if Q for my tea is a negative 500 joules, then Q for the surroundings must be a positive 500 joules. Or similarly, if I have a pot of water on the stove and heat is being transferred from the stove into my pot of water, then if the pot of water gains 1,000 joules, that must have meant that the stove released that. And so we see that the sign changes, although the number remains the same. One thing's gaining, one thing is losing. We're going to put that to good use. Okay, so here's the deal with calorimetry problems. They're really not that hard, but there's a lot of words. So the first thing you're going to do is you're going to take the word problem and you're going to list everything that you're told. And then you are going to look to see which of the materials involved in your calorimetry problem, because there will always be a system and a surroundings, you can calculate heat for. So what do you know? Mass, specific heat, and change in temperature. Then once you have a value for heat, you know that the opposite was what was either gained or lost by the other material. And you'll use the equation Q equals mc delta T a second time to solve for your missing information. So write that list down. And then let's go and work a problem so you can see how this actually works. In this problem, we have a block of metal. We know its mass is 29.54 grams and it has a temperature of 93.8 degrees Celsius. The metal is being dropped into 100 grams of water at 23 degrees Celsius. And the final temperature of the water and the metal is 32.5 degrees Celsius. We're going to calculate the specific heat capacity of the metal. So with this sort of problem, we need to first identify what are the two materials. So we have a piece of metal and we've got a calorimeter or a cup full of water. So we're going to start by making ourselves a little chart here. And let's see, for the metal, we know the mass is 29.54 grams. We know that its initial temperature was 93.8 degrees Celsius. As we keep reading, we know the final temperature of that metal is 32.5 degrees Celsius, and we know we're trying to find the specific heat of the metal. For the water, you were told that you had 100 grams and that its initial temperature was 23.0 degrees Celsius. Its final temperature is 32.5 degrees Celsius. And you know that the specific heat for water is 4.18 joules per gram degrees Celsius. You always know the specific heat for water, and you need to remember that. So as you look at this chart, it looks like I know everything I need to calculate heat for the water. So the first thing we're going to do is we're going to use the equation mc delta T for the water. So my water gained 3,971 joules. From a sig fig standpoint, I really only know 2, but I'm not going to round for significant figures until the very end of this problem. So at this point, since the water gained that amount of heat, I know how much heat the metal lost, the opposite. And if I know how much heat the metal lost, I can use that in the Q equals mc delta T equation, where my unknown will be the specific heat of the metal. Okay, so here's all of the work. So the specific heat for the metal turned out to be 2.2 joules per gram degrees Celsius. The last step in that math problem, what needed to happen was I needed to get C by itself, so I divided both sides of the equation by 29.54 and by negative 61.3. And that left me with my value of 2.2 joules per gram degree Celsius. So again, the core for a calorimetry problem is make your table so you can see what you have all the information for, find what you can solve for Q, flip the sign for the other material because you know that they're going to be opposite due to the law of conservation of energy, and then plug all the values into those equations for Q, the second equation for Q, to solve for your missing information. Let's take a look at one more example. So in this case, I've got a block of metal, and the specific heat capacity is 0.86 joules per gram degrees Celsius, and its initial temperature is 98.5 degrees Celsius. It's going to be dropped into 200 grams of water at 27.7 degrees Celsius, and the final temperature of both the metal and the water is 32.6 degrees. Our goal is to calculate the mass of that piece of metal, given the fact we know the specific heat capacity of water. Please remember the steps. Start by making a table listing everything you know. We're going to do that now. Once we have our table, we can figure out what it is we know enough information to calculate Q for. In this case, it is again the water. So we're going to calculate Q for the water. Once we know Q for the water, we know that's the amount of heat that the metal lost. And then once we know that, we can use Q equals mc delta T again for the metal. Doing all of the math gives us a value of 72 grams for the mass of that metal. We do have two significant figures, both from the change in temperature in the first part of the problem where we're calculating heat for the water, and from our heat capacity for the metal itself, and so we get 72 grams for the mass of that metal.